Hey, that's up here. I'm Zinasra again, and we're about to wrap up this course actually. So the last few things we would like to talk about today is going to be, hopefully this is going to be a very short recording. We're going to be talking about recommendations, suggestions, and best practices. And this is actually triggered by this quote. What would a mistake here be like? And I was thinking about this for a while and decided to have a few ideas and few thoughts put down just to see, um, most likely your thoughts on them and what we can do. These are very, very rough and abstract ideas, and most of them really come down from publications and my students and experiences. So this will be split under recommendations, and then we have suggestions, and we have best practices. Uh, so one of the main recommendations I have is continue to learn, you know, understand the difference between statistics and ML. So in the slides I have these numbers, then we'll go to the PDF and we'll talk about them more, like, a little bit in depth. We have to really understand and always remember, like, model assumptions, outcome, and limitations. Because this will help us a lot when it comes to decision making and understanding how the model was able to figure out what to do. I always recommend to remember not all models are black box models, or not all of them are explainable models or causal models. Maybe we may not need all of them, we may need one of them. We're always going to have some trade-offs. We're going to have some biases, and this has to be, like a cornerstone or a corner point to always keep in mind and recommend and remember. I always recommend to share your data and code whenever you can, because it helps out, having more people learning and practicing and verifying your work, creating databases. We don't have to reinvent the wheel for every problem. Some of the suggestions I have is, do your best to solve with simple algorithms, simple models. Have a few, up your sleeves and always think about these. Testing, try to come up with like some new ways to test your models. It doesn't always have to be with performance metrics. Training and testing, training and validation. These are all good things that we can verify model performance on. But I think there are like other things that we could do as well. So try to think about what other things we could work. These are generalized stuff. Like, these are general for almost every case, but perhaps for your particular problem, you may have like other things that you might value more than performance metrics, for instance. It helps to convert these models into web apps or like apps, because it allows people to use them a little bit, read more about them. Physics is very, very important for us. Mechanics, physics, all these things are important to us. So we can try to include them into ML whenever we can. And there is going to always be that we were just talking about trade-offs. Shall I use a small data set that's, I know it's good, or like a large data set where the data is all over the place? So try both and see. I would always value, balance and healthy data sets. And make sure you share your data, statistics and your data. Start simple with simple models. So maybe try not to jump into something very, very new or something that's very, very old before you go with something that's much more common. Black box models are, I personally, I think they're good, but I think that with whatever is going on right now, that we can have similar performance, if not better, with explainable models or with causal models. So maybe try to have start to think about other types of models instead of just jumping into black box models to create. And the last thing, and of course, my all over the place, we can always think about integrating ML into future works. And this becomes interesting because once we start to add it and think about it in the future research, you'll start to see that there is a lot of attention towards those tools. So if we navigate back to the PDF where I have more ink put into place, this is where I like define recommendations. So a recommendation, I think, is a good definition would be like an advice. This is something that I came across like in the open literature, or something I was advised to do, something we thought about. A suggestion is more like a personal opinion. So this is basically we've tried a few things in lab, and we found out, if you try this, you know, it could help you a lot later on. A best practice is something where we see a lot of it like in publications. So they would say, they wouldn't really specify, but if you look at like a number of publications, you see common trends there, like things that researchers seem or engineers seem to do. Most of the best practices I have here, actually, to be very frank, are from publications. I was hoping I would have something from like an industry point of view. So if you have any, please share them with me. That'd be great. However, the ones we have here still, I think, are applicable to a large extent to the industry stuff too. But it also helps to see what they think about ML. So for recommendation, my favorite first one is, of course, learn and continue to learn. Life doesn't really end by having a degree or like graduating. You can always do more. So learning becomes is one thing that uh, helps you a lot. Of course, you can learn a lot from by publications, by practicing, by doing all those different things that you could do. Your co-authors, social media. There is a lot of good stuff. Not all of it is good, but there is a lot of good stuff. And always remember, we really learn and we're learning about ML because there is a rise in digitalization. There's a rise in automation. A rise in automation. So the future is going to be, there's a very, very good chance that we're going to be doing a lot of ML in the future. Because if you think about surveying now, uh, everything is automated. Oh, not everything, but like a big component of it is being automated at the moment. We still see total stations and stuff, but we see more like drones and GISs and all those things. And there's a big ML component. There's a lot of startups now that use ML. So that was the big item, and one of the sub items for that item is always to it helps to look back and see, okay, well, how does ML really differ than statistics? Like, why can't we just continue to use statistics as we've been doing for a long time, right? Well, as we all know, we always have, positives and negatives for everything. And statistics and ML also have both of these sides. So it always helps to, go back to the drawing board and start to think about, okay, well, what can I do, or what can this thing do that, A didn't do, or cannot do, or I have limitations in A, well, how can B come and help and supplement with that? There is a big difference also between when we predict something through ML and when we predict it through simulations or tests. And whenever we do a test, there's going to be a hypothesis there. We're building a test to test something. We know what it is. When we do a simulation, there is a lot of physics involved, a lot of assumptions involved, idealization. Uh, Whenever we use ML, there's going to be a lot of data involved. So how does, prediction through data or data-driven prediction is a little bit different, and I'm putting this very, very lightly, than prediction using tests or numerical simulations. Because if you're building a numerical model, you're basically trying to build something, to predict something. You validate against a test, hopefully. But the goal is really to take the verified model and try to change some parameters and try to predict what would happen, because tests are expensive. In ML, it's a little bit different, as we've seen in the causality chapter and the data-driven chapters. So we have to be aware of those. Yeah, I see this a lot with grad students. And I think it's natural to want to try new things. Like, somebody have this new algorithm, you want to go and jump into it. Or somebody has been like, some of those methods, they have like buzzwords to them, IoT, deep learning, all those things. So we sometimes tend to jump into those right away. And I mean, I think trying something new is great, but you also want to remember that if we're trying to solve something, start simple and then grow from there. It could I think it has merit to try something new, like out of the box, but sometimes we don't really have to have very, very exotic models or complex models. Something that, has been simple, explainable, easy to use, like a decision tree or something, can help out a lot, versus something that's extremely intricate and may not give us, may predict the problem easily, but it just may take a little bit more time to try to set up, tune, apply, explore, figure out, optimize, and deploy. So remember, there's going to be both sides to everything. It'll be very, very interesting to see how we're going to navigate all these things. So, yeah. Number 5 is we always have to remember these things: model assumptions, outcomes, and limitations. It's important to know these. For instance, a key assumption in data-driven analysis is we have comprehensive and healthy data set. How many of those do we actually have, right? Yeah, this is one thing that you're gonna have to think about for forward. Whenever you get a prediction, we're gonna have to figure out, okay, do we need to know how the model was able to predict this? Do we not need to know that? If you look at the building code, we have equations there. Well, we know how the equations we arrived at those, whether through theoretical derivation, maybe statistical analysis or empirical analysis. How about ML? How can we explain these things? And something that's important, an explainable model is not a causal model. I really think this is important to also to realize. Because sometimes, even if you like reading papers in 2022, 2023, 2024 in engineering, you'll see a lot of the like writings. Whenever like you read some of those things, it kind of tell you that the model, because the model is explainable, we kind of know how this thing happened, and I don't think that's going to be always true. It's going to be vaguely true, I guess, because it's not always the same thing. An explainable model tells you how the model arrived at the prediction using your data. A causal model goes back to the DGB and try to figure out the DGB first, or like an assumed DGB, and then from there we can come up with a hypothesis probably. I think there is a very good chance where somebody could use an explainable model to come up with a hypothesis, but it's not the same way as a causal model because the assumptions are different, the limitations are different. So there has to be a linkage between these things. I think there is. Hopefully we'll be able to figure it out. So uh just like engineers, we favor some methods. Yeah, of course. We have this all, we have experimentalists, analysts, and machine learning enthusiasts. We tend to favor certain things, certain softwares, certain languages, certain behaviors. And I think this is fine. This is what makes us strong, actually. We don't always have to focus on one thing. We can always do multiple things at the same time. Performance metrics, I know we have like a big chapter on those, but the thing is, with performance metrics, or the traditional sense of performance metrics, is we're trying to evaluate performance based on, some accuracy metric for the most. I think this is one good thing. But I also think that we have other metrics other than accuracy that we have to focus on too. Think about functional performances. Think about physical performances. Think about other things than saying R square is this much or MAE is this much or that much. Our models are biased because we have our data could be biased. The way that we create the models are biased. So knowing these things is important. It's very important. Keep that in mind. Especially when you compare like publications or different models or different data sets. Always keep that in mind. Number 9 is, yep. So this is the space of features. And this is possible feature. This is known features or accessible feature, because sometimes we could know something, but we can't really access it or measure it. So finding out the sweet spot between all of these things, talk to experts. Talk to professors, engineers, senior engineers as well. There is a domain knowledge, physics, mechanics, especially. Go back to the things that you learned like when you were a sophomore. Most of the fundamentals are there. Remember those things and try to see how can I use this in my machine learning model? Because it's data, we're gonna have trade-offs. We're gonna have between variance and bias, complexity versus accuracy, explainability versus accuracy, different types of models. So try to pick your battles wisely. Yeah, I mean, this is extremely personal. I mean, I really think I see this a lot. You see, you're reading a paper, and then, like, in a few weeks from then, you find a paper on a similar title, a similar project, I mean, similar area. And they would say, well, this model has an improved performance of, single-digit percent than the first model. Sometimes when you're dealing with, let's say, accuracy of 95% or like even 90% or 85%, uh, maybe 80s or 70s if you have like 10% improvement, that's actually substantial. But when you're thinking about 95 to 96 or 95 to 99, the difference is really small. I mean, I don't know if it's worth the time to spend on those things. It could be also problem dependent, but let's say everything for general problem, general data sets. I think the difference in accuracy, a small difference in accuracy may not warrant it might be like as of a big deal as we think it is. It's improvements, yes, it could be something important, but I think we could spend the resources somewhere else, like for instance here, between 97 and 94, it's very, very small. Let's say the black box model is gives you 97%, next level model gives you 94%. Which one would you pick? Well, both of them are fine. I mean, accuracy wise, you're gonna have to see, okay, well, the experimental maybe gives me a little bit more. Maybe the black box model is a little bit faster. So you're gonna have to go back and see the pluses and negatives for the two different models, and then from there you would choose. Because in this case, I feel that accuracy may not be the metric to decide for. It could be other things, speediness, I mean fastness, explainability, maybe the black box model aligns more with physics if you look at the feature importance versus the explainable model. Yeah, whenever you can share your data and code, we have a lot of repositories that allow free publications, and you get like your DOI and people can cite it. So why not? Whenever you can do that. Suggestions. Hmm. Yes, start with simple algorithms. Yeah, we've talked about that. It's like learning. You go to statics, then mechanics, then theory, then design. Same principles apply here too. Yeah, no freelance theory. It basically says that we don't really have algorithms that are much better than other algorithms. If you take the average of all algorithms, they tend to be perform, equally well. And this also opens up the invitation for trying different algorithms, trying different metrics, see what you can go from there. Explore. Explorations is not bad. Good. Yeah, remember where your data comes from. Remember you have. Oh, yeah, this is the old. You usually deal with this a lot in applications. What uh, there has been a trend of somebody would they have like an experiment and they create a simulation or like a numerical model, and then they use the model to create thousands of data points that then they teach a machine learning model on the simulated data, and you come up with stuff. What I think it's a good way to do this, but I don't see a lot of attention being paid to. Whenever you build a numerical model or a FE model, there is a lot of idealizations in the model, material models, boundary conditions, element types. Some elements account for, I don't know, cracking or creep, others don't. So all these things, they have an accumulated effect on the accuracy of the model. Because if you think about experiments, they don't really have a lot of idealizations as many as those in numerical models. So if the data is inherently has certain things that we can't really get out of, or a lot of idealizations, it would affect the ML model for sure. And the ML model is really going to hit 100%. You're gonna have those issues as well there. Everything is gonna accumulate. What I'm trying to say is I don't think it's a bad idea to do this. I think it's bad if we ignore the origin of the data. So we have to keep that in mind. Yeah, whenever you can, test your model as much as you can. Yeah, think about other things than training validation. Maybe think about functional items. We number six, we don't really see this as much, unfortunately. Most of the models we have are, we keep them and we publish them and they're just, left in publications and stuff. Very few are actually deployed. I think what 26 is, yeah, citation 26. About 90% of the models are never deployed. That's a big percentage. A lot of work to do just for a publication or like for a course or for a project. I think there has to be a way that we can create these models and use them and then maybe transfer them for other things. Yeah, we've talked about those apps. Physics is important, mechanics is important, principles are important. Yep. Best practices. Try to use high quality data. High quality is good. And always think about this. Whenever we're using algorithms, there is really very small room to tune the algorithms. Uh, there is a lot of room in the data if you can. I don't know why my chair is a little bit low. I feel because the screen was usually up to the side. So there is very small room for tuning algorithms. The algorithms we have actually work very well. We have a data issue most of the time. Data issue. Yeah, this is actually good. By the way, about 50% of our publications in 2020, 2021, I think Arash had this paper. We have these algorithms. ANN, genetic algorithms, genetic programming, SVM and PCA. These are the ones that very often come across these papers. Same thing for training. We use a lot of cross-validation, but then we use much, much more in splitting. 70 to 80% for training, 30 to 20% in validation of testing. Very, very common. Very, very common. Even performance metrics. We use a lot of these metrics. These are the top five. You see them in almost every application. May, MSE, R square, RMSE, and MAPE. We have, out of everything else we've learned in the metrics chapter, we tend to use these metrics a lot, or most of the time. So all of these things tell you something because it tells you that there is a lot of focus in your network. But it also tells you something else. I know I don't mention this a lot, but whenever you do we try to see what the domain does, you go back in time, you'll say, okay, this is between 2011 and 2021. There is a lot of papers that uses ANN because it's a very standard and older kind of algorithm. And if you do, let's say, if you do an analysis in 1980s and 1990s, probably you won't see much of those fancy XGP because I don't think it was even invented by then. These are all much more recent algorithms. I guess maybe in 10 years from now, these will shift a little bit because you'll start to see a lot of XGBoost, LGBMs, and all those cat boost models there as well. It will no longer have the same. Yeah, these are all publications breakdown. Yeah, report statistics in your data, integrate ML. Yeah, this is this is personal. This is for me is personal. Try to use explainable causal models whenever you can, unless the goal is to create a black box model. Sometimes it's the goal. You have a small problem or like a routine problem, and you just predict it. You don't have to think much about it. I like this movie. Which one? This one's 35. I would highly advise reporting ML. Yep. Yep. I know a lot of departments are like, a bit requirement was not possible. If you listen to Cooper, it's necessary. Yes. Now it's very important. I think there is a lot of schools that are pushing for ML. Even A, but they have now like I think a requirement for data science classes. It will change. So it already is. There are going to be more changes. So, chapter 11 is very short actually. It just talks about like very rough ideas about things we do now, things we expect to have in the future. Big and small data sets, imbalanced data sets, like what can we do for those? Learning, machine learning. We have a problem with benchmarking. We have to have benchmark models that for us. Of course, standardization is a big issue. How can we use ML in building codes? That's a big item. Can we have a methodology for ML for all of us to use, like one consistent methodology? Popularizing ML is big now. I don't think it's. I think that what we need is education, popularizing the education and integration for now. Engineering ML, of course, it would be great to have our own algorithms for our own problems. That help us a lot because instead of taking an algorithm that's a general algorithm, we can create one that's specific for specific problems, and hence we can have a lot of probably improved accuracy and all those things. Possible ideas. If you have like ideas about, let's say, like for theses and all projects and stuff, here's some. But of course, my favorite thing is the following: find a problem in your area and then go from there. Well, I think this is it. I hopefully this was an interesting course. I know some lectures were a little bit more than 60 minutes. I apologize for those, but you could always, pause them. You know, 20 to 15 minutes is usually my limit when it comes to learning something. I usually pause and do something and then come back for it. As always, if you have any questions, please reach out to me. Let me know. If you find any of those knickknacks or typos, also let me know. If you happen to have like very cool data sets or codes that you'd like to share with me, that'll be great. Hopefully, we'll integrate those into the next edition. I would love to meet and talk. Until then, continue learning, and hopefully everything works out well, and we'll get to do more ML soon. Thank you very much.